Okay, let's look at some more of these problems here. We can get into some more nasty looking problems. And what they're doing is playing off, well, do you need the chain rule? Do you need the product rule? Do you need the quotient rule? And the answer is, if you can avoid it at any cost, please do. Because it is not easy for antiderivatives for all of those rules necessarily. It takes multiple steps, there's different rules, there's different procedures, and it's not so straightforward as finding the derivatives. So you have to be able to think, how can I rewrite these? So for instance, what you can look at, for the first one, it says find the antiderivative of 2 over the square root of x dx. What I would think about this as is I would pull out the 2 and I'd make this the integral of, and I'm going to want to use the power rule, so I need to think of this as x to the negative 1/2 with respect to x. Now I can actually do my integration, right? So this would be 2 times, well, what's the integral of x to the negative 1/2? Using the power rule, I would say it's x to the negative 1/2 plus 1, which would be x to the positive 1/2. Again, though, I need to divide that by the exact same power, so that's divided by 1/2, plus c. Well, let's go ahead and simplify that. If you simplify that, isn't that the same thing as 2 times, well, wouldn't that be 2 root x? Well, isn't that really 4 root x? And then we need our plus c as our final answer. So we should have 4x to the 1/2. I don't know why I chose that one back in radical form. I would have been perfectly happy if you left it as 4x to the 1/2. You did not have to go to the radical form. What about something like b? Right? If this was a derivative, we would be thinking chain rule. Drop the 2 inside the same, power minus 1, derivative of the inside. But the problem is this isn't the derivative rule, this is the antiderivative. And we don't have an antiderivative rule for the chain rule yet. So we need a different idea. So what can we do? Well, couldn't we expand this? It's only a square, and squares aren't bad. Isn't this really t squared plus 1 times t squared plus 1 with respect to t? So wouldn't this really be the antiderivative of, well, t squared times t squared would be t to the 4th, and then you'd have plus t squared, so that'd be plus 2t squared. Then you'd have 1 times 1, so that'd be plus 1 dt. So couldn't we just expand it and say this is the same thing as the antiderivative of t to the 4th plus 2t squared plus 1? Well, what do I do there? I integrate each term individually. The integral of t to the 4th using the power rule would be t to the 5th over 5, plus the integral of 2t squared would be 2 times, well, t squared would be t cubed over 3, plus the integral of 1, that would be just t in this case. Of course, then you need the plus c. So you want to simplify it now. Well, there's not really too much to do here. This would just be like, what, 1/5 t to the 5th, I guess, if I want to write it as a fraction, plus 2/3 t cubed plus t plus c. Again, I should be checking my answers for every single one of these, and I strongly encourage you to do that. How about something like c, where it's x cubed plus 3 all over x squared? Well, couldn't I just separate that? Couldn't I look at this because it's only a single term on bottom? Anytime it's a single term on bottom, I want to think about separating it. So it'd be x cubed over x squared plus 3 over x squared. Well, isn't that the same thing as the integral of x cubed over x squared is x, plus this would be looked at as 3x to the negative 2. And I'd be integrating that with respect to x. So when I integrate it, I can integrate each term. The integral of x is x to the 1. So x is x to the 1, so that would be x to the 2 over 2 plus 3 times the integral of x to the negative 2 would have to be careful with this, x to the negative 2 plus 1 would be x to the negative 1 over negative 1. Then we have our plus c. So let's simplify that. What would that be? I'd have what? 1/2 x squared minus 3 over x, if I put it in proper form. Minus 3 over x plus c. Never forget your plus c, or I have to take off credit. Okay. Let's keep on going here. How about the integral of the cube root of x times x minus 4? Do I have to use something like the product rule in reverse? And the answer is, well, no, not on this one. This is really the integral of x to the 1/3 times x minus 4. And that's something that I can distribute, right? So this is the same thing as the integral of, well, x to the 1/3 times x. It's 1/3 and 1 is my powers, and when I multiply, I add them. So 1/3 plus 1 would be 4/3. and then it would be minus 4x to the 1/3. I can integrate that with respect to x. So when I do that, let's use the power rule. This would be x to the, well, it's 4/3 plus 1. Be careful with your fractions there. Please use your calculator. 4/3 plus 1 would be what? 7/3. But then I have to divide by that exact same number. Minus 4 times x to the 1/3. So I have to add 1 to that. 1/3 plus 1 would be x to the 4/3. But again, I have to divide by that exact same number. Okay? So what do I do here? Well, remember, dividing by fractions is the same thing as multiplying by the reciprocal. So wouldn't this really be 3/7 x to the 7/3 minus 4 times 3/4 x to the 4/3? And the only reason I did that is to show that the 4's simplify there. And when I do that, what I end up with is 3/7 x to the 7/3 minus 3x to the 4/3. And then, of course, I need to add my plus c to my final answer. You guys might say, yeah, there's plus c, but I'm telling you that's one of the most forgotten things on the test. And I cannot give you credit unless you remember plus c on the test. You must remember plus c. I'll write the note again. I can't write that note enough. Must remember plus c. I'm also going to write another note. Please check all of your answers. So, what do you do to check your answers? Again, just differentiate every single one of your answers. Every single one of those in the box, you're going to find the derivative of. And when you find the derivative of it, it should be the same as the original problem. So I've been checking all of my answers in blue up to this point. To save time with recording, I'm not going to check those answers, but I beg of you, please, please, please do. I should see that work on your paper. I should see that work on your extra practice problems. I should see that work on your test. You should know whether your answers are right or not. So we have this idea of antiderivatives, and we have this idea of plus c, which is called the general solution. We know that there's an infinite number of answers because we can add or subtract any constant because the derivative of a constant is 0. So yes, there's always an infinite number of answers. But what if I don't want an infinite number of answers? And a beautiful way to figure this out or to think about this is to think about it graphically. So what are we doing when we add or subtract a constant graphically? Well, graphically, what you're doing when you add or subtract a number is vertically shifting the graph up or down depending on whether the constant is positive or negative. So for instance, if we wanted to find the antiderivative of 3x squared minus 1, well, that would be 3. If we found the antiderivative of it, it would be 3 times x cubed over 3 minus 1 times x plus c, right? Well, that simplifies into x cubed minus x plus c. So the idea is we know that the bulk of the answer is x cubed minus x. That would be the function, the parent function. We add this plus c as saying that, look, you can add or subtract any given constant, okay? Well, let's look at the graph here. What if we actually took the graph of x cubed minus x? What does the graph of x cubed minus x look like? This right here, sorry, I thought I had the highlighter. This right here is the graph of x cubed minus x. That would be a constant of 0. That is our answer, x cubed minus x. What the plus c does is simply shifts it up or down. So what we might be talking about is, look, we want that curve, but we want that curve that goes, we want a specific one of those curves. And so what they're doing right here is they're talking about, well, let's read here. It says, each of these antiderivative is a solution to the differential equation, but then it says the particular solution is what we're talking about now. A particular solution means we no longer want plus c, and what they're saying is they want the particular solution that has, when you plug in 2, you get 4. In other words, it goes through the point 2, 4 is what they're talking about. So what we have to do is we have to find which one of these curves goes through the point 2, 4. And they were able to find that curve right here. That's when we have a constant value of -2. That's the curve that went through it. So again, if you notice, the first part of our answer is exactly what we knew it was, the x cubed minus x, but to get to the particular solution, our constant needed to be -2. So that's called finding a particular solution. I know the general answer, but I want this specific version of the answer, this specific one that goes through this exact point. We're going to find out what C needs to be. And again, that is called a particular solution. So in the next examples, what we're going to do is figure out, what do you do mathematically to find the blue curve? We know we have the general answer, the red curve, in any vertical translation of it, up, shift up or down by adding or subtracting against. How do I find that blue curve? And that's what the next problems are about.